Thank you very much. And thank you all for staying for the last session here on a Friday of a holiday weekend, so I appreciate you staying for my session. Thank you very much. In this session, we're going to talk about OpenFlow and the progression to the version 1.3 standard. And then I'll bring to you some of my knowledge from working within the Open Networking Foundation as the testing interop chair, and what testing has been done to this point with version 1.3, as well as some basic test methodologies and capabilities Ixia offers to test OpenFlow. So there's usually a mixed skill set in the room. Some people know a lot about OpenFlow, some people know very little. Some people understand software-defined networking at a high level, but don't understand maybe all the components. And so I just have two brief slides to help educate you on software-defined networking and what component of that is actually OpenFlow. So if you look at the architecture for software-defined networking, the primary definitions it says is a separation of the control plane and data plane. So instead of distributed protocols like BGP and OSPF running router to router, instead you're abstracting that and running it in a centralized mode through the control layer. And then the control layer is programmable via well-known APIs that is known as the application layer. So software-defined networking is really kind of a three-tiered model of applications, control plane, and then the data plane. OpenFlow as a protocol is really just one component of that, which is this southbound API. So in this architecture, this is referred to as a southbound API, and these are defined as the northbound APIs from the controller. So OpenFlow is well-defined and standards-based because it's published from the Open Networking Foundation. The northbound APIs at this point are not standardized. So that does have some implications on OpenFlow, is that if I develop an application for one controller, it's not necessarily directly portable to another controller because the APIs may be different. But OpenFlow is standardized upon, and that's this program language here that allows the control layer to tell the network what to do. And there's many benefits to move to this model, I'm sure most of you are aware of, but basically you have more control of your network and network layer. So on the next slide here, we're talking about the basic fundamentals of OpenFlow. OpenFlow defines two components, a controller and an OpenFlow-enabled switch. And these two devices talk to each other over a session, and this is called the OF channel, and this is a TCP session which can be encrypted, but basically it's a channel where the controller can talk to each one, and it pushes down messages which are known as flow mod messages, and it's populating the flow table with basic commands of match and action. So match on this field of the packet coming in and take this one or more actions. So that's the fundamental basics of OpenFlow, and the controller has a session to every switch in the network. So a good analogy is like the switches become like line cards, and then you have a centralized controller card. So it's like a distributed router or distributed switch style of architecture. When you look at the progression of OpenFlow, it originated at Stanford, and the 1.0 specification was first published in 2009. Stanford moved forward with version 1.1, and at that time there was a lot of interest in OpenFlow. However, it was just in the research communities. And they said, how do we take this and make it more open so that more vendors will implement OpenFlow? So they thought about standards bodies like IETF or IEEE. They decided to create a non-for-profit organization called the ONF, Open Networking Foundation. And the intellectual property rights of OpenFlow is now owned and controlled by the ONF. So that's important, and it's a member-led community. So the ONF has produced the 1.2 standard and then moved right on to the 1.3. And now the 1.3 is what they've recommended for vendors to implement because it's a stability build. They're adding features and fixes to ensure that 1.3 is the most stable build. So most equipment manufacturers that are implementing OpenFlow have moved from 1.0 to 1.3. And You see 131, 132, 133 is about to release. These are just minor updates and fixes, but they're compatible. If I just advance one, you see that the ONF itself is not just working on OpenFlow now. They're looking at the bigger picture of the northbound API and the overall architecture of software-defined networking. They're looking at the management. They've defined OF config to bootstrap a device. That same group is beginning to work on OAM, a very important component that's lacking in OpenFlow right now. The extensibility group is advancing the standard. Market education is promoting OpenFlow and educating OpenFlow. Forwarding abstractions is working on defining how OpenFlow can run on different hardware. Optical transport is quite interesting because OpenFlow is becoming a protocol that can be used to control the optical layer. So companies like Adva, Sienna, Cayenne, and others are, Fujitsu is in there, are looking at using OpenFlow to configure and provision the optical layer. And then there's testing and interoperability, and I'll go into more detail on the work we're doing there. In this next slide, I wanted to bring this out so that the engineers in the room get a better understanding of how OpenFlow works. And OpenFlow establishes a session, right? There's a TCP session. Then there is a basic hello message that handles the version negotiation. Then there's a feature request reply, and then echoes are exchanged to keep the session open. So with this ladder diagram you see, that's all it really takes to maintain an OF channel session. Once that session is up, it uses configuration commands like flowmod to populate the flow table entries. The switch can also communicate up to the controller as well via a message known as a packet in. So a packet in could be sent up to the controller can process it, make a decision, and push down a flow mod. This is kind of so that you know OpenFlow is really just a low-level command set. It doesn't have a lot of intelligence. It doesn't have methodology. It just is the command set that allows the upper layer applications that run on the controller to program the network. So OpenFlow 1.3 changes the protocol quite a bit from 1.0. So the reason I'm kind of focusing on 1.3 is it's what most equipment manufacturers are moving towards today. Several have released it, and we're beginning to test it now and look at performance and capabilities of 1.3. So there's many changes to the OF channel itself, that connection. First is that the switch capabilities have been extended with multiple tables, logical ports, all kinds of different information. So now you can't just use a feature request reply to get all of the information about the switch. So there's an extended number of commands known as get config that the switch can get, the controller can get all the configuration information from the switch. So it understands its table capabilities. It understands logical ports like tunnel interfaces. 1.3 addresses a major problem of 1.0, which 1.0 defines a single controller. So you'll have issues with redundancy, resiliency if that controller goes down. So 1.3 formally defines the ability to have multiple controllers, a master, slave, or equal role, and that addresses redundancy and resiliency. 1.3 refines the messaging handling between the controller and the switch, adding something called a multi-part message. Because oftentimes the controller wants to get information from the switch, like I want the port stats, the flow table stats, the description. It wants to collect a bunch of information. So it can do this via a multi-part message saying, part 1, give me this stat, part 2, and the switch can acknowledge each one of those messages. Because what was happening previously was the controller is just sending a bunch of get commands, and the switch can't respond. It gets too busy, or it's not prioritizing the message, and it either doesn't respond or it responds with an error, and the controller has to start all over again. So the multi-part messages helps that communication. Another important addition was, I've talked about all the messaging is handled over the TCP session. Well, the issue is that many switches can have parallel processing. They can have other engines that are handling functions. So one way to offload some of those functions is to bring up auxiliary connections. So this is another connection from the switch up to the controller, and you can offload certain functions on that. For example, you may have a lot of packet in and packet out messages being exchanged from a switch to a controller. And you can move your packet in, packet out processing over to an auxiliary connection. And then one more, as I began to mention a little bit earlier, is that it formally defines logical interfaces. So your switch may have other interfaces besides its physical interfaces. A perfect example is a tunnel interface. If I want to match on a destination MAC address or a IP address and then do a forward onto a tunnel interface, that would be a logically defined interface on the device. So moving forward into the flow table changes, 1.3 changed flow tables quite a bit. It defines multi-table processing. So multi-table is not mandatory. In fact, at the PlugFest, we had a number of devices that supported version 1.3, but single table only. Other devices supported a certain limitation, like 3 tables. So when it comes to multi-table, you may have very different implementations between devices. However, the implementation or the capability of having multi-table allows for more complex processing by the device. The next point is that OpenFlow is kind of fundamentally based on match and action. Match on some field of the packet and then take an action or multiple actions on it. 1.0 defined 12 fields. Those Ethernet, IP, single VLAN tag, the ingress port. It was pretty limited. Now at version 1.3, it defines 40 fields. So it adds MPLS header, provider backbone bridging, VLAN stacking is supported, or Q&Q. IPv6 is supported. So you have 40 header fields that you can do match on and various actions, but of those, only 13 are mandatory. 27 are considered optional. So again, it's important to understand what fields the device supports. At the PlugFest, we had some devices that supported IPv6 but did not support MPLS. We had some devices that supported most actions but didn't support rewrite of MAC address. So you may find with a lot of the OpenFlow specification as being optional that the implementations will vary depending on what they were designed to do, as well as potentially what hardware they're running on. The next point is that OpenFlow adds something called a group table. The group table is useful for multicast processing, as well as you can use a group for things like link aggregation groups. And finally, one other change is that meter capability per flow has been added. And so what a meter can do is essentially rate limit. So this can help you to implement QoS in an OpenFlow network. You can also meter packets going up to the controller. So if you want to implement rate limiting so you're not overwhelming the controller with packet in messages, you can actually use a meter and rate limit traffic going up to the controller. So on the next page, I describe OpenFlow changes to the statistics. So when you add all those features, you need to be able to get the configuration for those features as well as the statistics for those features. So you need statistics for your group table. You need statistics for your meter table. So there's a lot of additional components so the controller can get configuration and manage and monitor those features. So this slide, I feel, is one of the most important in terms of understanding OpenFlow, is that when you have an OpenFlow device, it can run in pure software. OVS is a kind of a de facto standard where Open vSwitch is available, and it's a software-based switch that supports OpenFlow. Then you have existing routing switching platforms that are adding OpenFlow support. So this is good. They're typically hybrid-based devices, and it allows you to begin to use or start to test and play with OpenFlow and environments without, making a full commitment to it. And then the third category are more where OpenFlow is running on hardware that's designed for OpenFlow. And via the spectrum of devices, the software-based devices are low cost and full-featured, but they are limited in terms of forwarding performance. When you look at existing routing switching, they're going to be the same price point, but they're going to have a subset of features because they're running on existing hardware that was not designed for OpenFlow. So they may not be able to do multi-table. They may not be able to do certain matcher actions because of the underlying chipset they're running on. When you move to the new hardware-based products, then you are going to get purpose-built products for OpenFlow. So you probably get the best performance, best features. However, from a cost standpoint, you may be paying a premium because it's programmable hardware. So Intel has a programmable platform. NEC is leveraging programmability in the flow table that are purpose-built. So in some of these platforms, you'll have rich capabilities. However, the price point, it's not the same as just running software on some off-the-shelf commodity switch. So in the next slide, I want to just talk a little bit about what ICSI is doing and working on through the ONF. First is, we're the first test company to join the ONF back in 2011. And we immediately realized there was a need for testing. So we proposed the creation of the Testing and Interop Working Group. And this working group that we've been working on for several years now facilitates plug fests, or the interoperability events, to see how different implementations work together. We define conformance. We've, at this point, completed OpenFlow 1.0 conformance. We've published that standard. The conformance program is underway. The very first vendor has gone through that conformance testing and will be announced shortly in terms of being conformant. And we're moving on to version 1.3 conformance. We already have more than 400 test cases defined. So those are very important aspects. We're also looking at defining benchmarking methodologies as well. And those will start to come out towards the end of this year and more beginning of next year. So on the next slide, I want to kind of take you into what we do at the PlugFest. So this is an example network that we built that all the devices here, in the last PlugFest in June, we had 11 devices that supported 1.3, 11 switches that supported 1.3, and we had 9 controllers. So what we do is we build the reference network with access and core devices, we interconnect them, and then each controller gets a period of time on the network to test OpenFlow, to test their applications. So we tested in this case, to discover the topology, you can either use a topology discovery like LLDP, or you can talk to a database. So far in the PlugFest, we've not used database we've always tested discovery. So we run LLDP discovery to discover the network. We test things like layer 2 path provisioning, layer 2 learning via MAC address learning. We tested equal cost multipathing. And we moved on to version 1.3 features like testing MPLS, testing IPv6, trying to test multi-table implementations. And this is where it was quite challenging because, as I was mentioning before, some devices supported IPv6 and others didn't. So when you went to build the topology, you had to ensure that you could get something working end-to-end, because once it was provisioned, we would validate it with data plane traffic from the test products. So, there were quite a few bugs and issues that we're finding, and these are helping the participating companies improve their implementations, but also helps the controllers, because sometimes the controllers make assumptions. An example is with learning, you can make the assumption that an unknown packet will be forwarded up to the controller. It's considered a table miss. Well, some devices, when they don't have a table entry, they just discard the packet. So the controller vendors had to know that they have to insert a specific rule that says, for discovery, forward it up to the controller. So it was an interesting exercise because you find that when you read the specification, some vendors say, well, it's optional, you know, and so it ends up with some interesting challenges. Finally, we were testing the conformance frameworks. We have conformance frameworks available for 1.0 and conformance frameworks beginning to become available for 1.3 that have a subset of the testing. And as I mentioned, we've launched the ONF conformance program. So what I encourage you to do, especially the operators in the room, is that when you're working with your vendors, ask them if they're going to become ONF certified. Because if you go through certification, it's guaranteeing a certain level of testing that they are, conforming to the standard. So in the June Plug Fest, one of the first things we did with the network was we used the Ixia controller. Because Ixia, we make a test controller. And with that test controller, we have very specific control of the flow table entries and can validate on the data plane with our traffic generation. So we tested discovery, we tested layer 2 of forwarding, we tested many different features and components of version 1.3. And again, via testing with test equipment, it helps us to isolate and understand and identify issues and problems. That way, when we move to a production controller, we already understand what the problem is if one vendor wasn't handling the messaging correctly. And in many cases, we identified issues early on in testing, and then the vendors were able to fix those problems, and by day 2 or day 3, they were up and working with the production controllers. So it was very good progress there. So getting into what Ixia does with OpenFlow, we really have a 3-part solution. First and foremost is just ensuring that the protocol is conforming to the standard. So we have a conformance framework called IX Anvil. And IX Anvil has support for hundreds of protocols. So it's just another protocol we've added into this framework. So we have OpenFlow 1.0. We're in alignment with the ONF specification. We also have an early release of OpenFlow version 1.3. And we will be adding to that the end of this year and beginning of next year to ensure we're in alignment with the ONF. The next component of it is for performance and functional testing and scalability. We've added OpenFlow into our IX Network framework. So those of you who use Ixia, IX Network is our software that controls our hardware, and it already has for many years protocols like BGP and OSPF and many others. We've added OpenFlow to it, and with it, we can emulate a controller. We can also emulate switches to test a controller. So we've had 1.0 out for quite a while. Earlier this year, we released OpenFlow 1.3, and we're continuing to add feature set upon that as well. The final piece of the puzzle is being a test company. We feel it's very important to understand performance. Because as I mentioned, if you're running OpenFlow in a device that's forwarding in software, you may have good functionality, but you may not have good forwarding performance, right? And even devices that we were testing, an example is one device was forwarding layer 2 in hardware, but layer 3 in software. So you had good performance for MAC layer forwarding, VLAN layer forwarding. As soon as you were trying to forward IP packets, the performance was quite low. So these are important things to understand as you're looking at deploying OpenFlow and supporting multiple services like MPLS or VLAN or IP-based services in an OpenFlow network. This next slide shows that many people know Ixia as being a hardware-based product. And this is true for more than 15 years. We have products that are built based on FPGA for wire rate packet generation, as well as multi-core CPU for protocol emulation. So we still have this and are the industry leader in 1 gigabit, 10 gigabit, 40 gigabit, 100 gigabit, all available today. What many people don't know, and it's becoming much more popular now, much more important now, is that more than 5 years ago, we took our Ixia technology on the port and virtualized it. So we can actually run an Ixia port in software as a virtual machine. So this is very important for OpenFlow, as well as when OpenFlow is coming together with things like network function virtualization, where you have a vSwitch, possibly a virtual router, a virtual firewall, a virtual load balancer, and sometimes you're not mapping to the physical world. Sometimes everything is VM to VM. The previous presenter from VMware was talking about that. Well, in addition to provisioning and spinning up your virtual appliances and using OpenFlow, let's say, to provision your path, you can spin up Ixia ports to then test and validate that in a virtual environment. So this includes both data plane validation as well as protocol validation for L2 through 7, so stateless or stateful traffic. So I'm a little short on time, but I just wanted to go through a couple more quick examples of what these solutions look like. With IX Anvil, we sit on a server or the Ixia hardware. We emulate a controller and can functionally validate all of the OpenFlow messages and validate or verify them on the data plane side as well. So again, Anvil has conformance suites for 1.0 and 1.3 in early release already. As you look at the second use case here, when Ixia emulates a controller, we can do very advanced features like testing discovery. And again, testing of discovery is a very important component because this is how the controller learns the network topology. So it can, process these, propagate LLDP, and ensure the device is properly handling the LLDP so the controller can learn the network topology. When you're looking at the switch performance itself, you want to push down the various flow table combinations, again, based on what you're going to use in your network. And the more complicated flow tables involve matching on layer 2 headers and layer 3 at the same time, or a combination of fields. You're going to have different performance if you're just doing VLAN-based table match, or if you're matching on a MAC, a VLAN, an IP, multiple fields. And then when you're doing an action, like adding a VLAN tag or changing a QoS value, Ixia can generate it and then validate on the receive side that the DUT is properly modifying the packet. Finally, in this use case, we're just showcasing the fact that Ixia can also emulate switches to test the controller. This is very important as well because many times controllers are running in virtual machines. You have to right-size the controller in terms of the CPUs you're allocating to it. And you need to understand that when it's stressed with packet-in messages coming from the switches, how can it handle it? It's maintaining the TCP sessions and potentially the auxiliary connections, but now it has to handle all those messages coming in. And when there's a change in the network, there may be a flood of packet-ins coming to the controller that it has to handle. Finally, benchmarking. I talked about this before, but one of the most fundamental things you want to do is be able to understand the forwarding performance when using OpenFlow. So again, the Ixia controller will push down flow table entries, and we can ramp up the table entries in a step mode or in a binary search mode. And we will keep adding flow table entries until we get an error from the switch saying table full. Then we can clearly understand at what point we're maximize the table. At each step, we can also generate traffic to see, okay, are these table entries in hardware or software? So we can validate the forwarding performance. So this was a 30-minute version of a much longer presentation that we go into more methodologies, more test cases. We have an upcoming public seminar that you can attend October 4th. So if you're interested, please register for that session. As well as this presentation material, also we have links to webinars we've done with HP and Intel. We can provide you links to that collateral in terms of more information on how to test with Ixia. So again, I thank you very much for staying on Friday for the last session of a holiday weekend. I hope you learned about OpenFlow 1.3 and how to test using Ixia. Thank you.